Hey everybody, welcome to the final review. Here we are. This one is for all the marbles. So please do your best to study as much as you can. We're going to go over some practice problems from a previous final in a different class, but very similar to our own. And yeah, let's just dive in here. So what we've got is an Excel file, and you can either choose to work with this stuff in Excel if that works best for you, or you can work with it in R if you'd prefer. I'm going to mostly be working in Excel. So what we've got looks like we've got 16 participants. There's three different clubs: psychology, chess club, and yoga club. If they own a car or not, happiness in a couple of different months. If they live on campus or off campus, GPA, and number of parking tickets. So we've got some good data to work with here. Now, let's check out some questions. So, what is X bar for happiness in March? Now, obviously, you need to know that X bar is the sample mean, right? So, what's the sample mean for happiness in March? Well, if we want to go over here, then you're going to just type in equals average and drag across all the values, and boom, you got 5.69. 5.69. That's pretty easy. 5.69. Okay. What's the sum of squares for happiness in January? The sum of squares for happiness in January. Okay. Sum of squares, SS. There's a function for that. Sum of squares, but we're actually going to have to get the deviation scores first, aren't we? So I'm going to right click and click insert here. And what we need to do is get the deviation scores. So I'm actually going to have to calculate the mean, aren't I? So I'm going to have to go equals average of the happiness scores. Click enter. So we've got the mean. Now I can find the sums of squares if I have the deviations from the mean. Okay, so what do you have to do here? Equals the first score minus the mean. You've got to put in these dollar signs around that so that Excel doesn't get confused. And if you drag that down, boom, you get all the deviation scores. So this is the deviation for each person from the mean, and let's see if that makes sense. 5 minus 2.5-ish should give us around 2.5, so that seems to make sense. 3 minus about 2.5 should give us around 0.5, so that makes some sense. Okay, so then you're looking at calculating the sums of squares. Well, sums of squares is literally when you take all of the deviation scores and you square them and then you add them together. And there's a function for that. Equals SUM SQ, sums of squares. So it's literally squaring all of these values and then adding them together. So the sums of squares for happiness in January is going to be 45.94. Whoops. 45.94. Okay. What's the variance for GPA? Okay, what's the variance for GPA? So we got GPA over here. Well, to find variance, I'm going to show you I've got all these equations, and these are pretty much most of the equations you'll need for the exam, the final exam. So you can see there's quite a few that we've done this semester, which is impressive, right? You are going to know how to use all these by the end of the class. So here's the equation for standard deviation. This is standard deviation. Variance is almost identical to this. It's just that you don't have the square root symbol. If you s squared means you square this, which just means you take away the square root symbol, and then you have basically what's on the inside. So you can see that it's the deviation scores squared and added together. That's the sums of squares up here, divided by n minus 1. Okay, so sums of squares divided by n minus 1. But guess what? There's also just a function for the variance, which is pretty nice. So we can do it a couple of different ways. Equals VAR dot S. VAR dot S would be the variance for a sample, which is what we have. So the variance is going to be basically 0.60. If I wanted to, I could calculate the sums of squares, like how we did for happiness in January, and then just divide that number by n minus 1 because sums of squares divided by n minus 1 is the variance. So you can do it a couple of different ways. Obviously, just using the function for variance is going to be the quickest way. So the variance was 0.60. If I have 8 parking tickets, what is my z-score? Parking tickets is 8. What is my z-score? So now this is not asking you to do a z-test because we're talking about only one individual person's raw score. If you only have one raw score, you're just talking about a z-transformation. If you have an entire sample average, then you can do a z-test, but that's not what we're talking about here. This is just, I've got 8 parking tickets, that's my raw score. What is my z-score? Remember, z-scores are in units of standard deviation. So how do you calculate a z-score? We're looking right here. A z-score is equal to the raw score minus the sample mean for that variable divided by the sample standard deviation for that variable. Okay, so we're looking at parking tickets, right? 8 parking tickets. Okay, so parking tickets. First thing we need to do is find the mean. This is going to be the sample mean, so equals average. Beautiful, we've got that. We also need to find the standard deviation. Okay, equals STDEV dot S, standard deviation. And now to find the z-score, all you do is take the original number, which in the prompt was 8. So if I have the raw score of 8, then you subtract the sample mean, close those parentheses off, divided by sample standard deviation for that variable, and you get a z-score of 2.50. Now, what does that mean? That means that if I have 8 parking tickets, keep doing that, sorry. If I have 8 parking tickets, if I have 8 parking tickets and my z-score is 2.50, that means that 8 parking tickets is 2.5 standard deviations above the average, above the mean for parking tickets of my sample. Okay? All right. Let's do it. I think that students who are in the chess club who also have a car have a higher GPA than members of the chess club who don't have a car, as well as all other students in all other clubs. Okay, what test will I use? Well, this is using chess club, which is a categorical variable. And if you have a car or not, chess club, so club, there's 3 levels. Car, there's 2 levels. These are both categorical. And it's asking about GPA, which is a numeric variable. So it's two factors, 2 categorical independent variables, and a numeric dependent variable. Well, that is going to be a factorial ANOVA, right? That's going to be a factorial ANOVA. 2 different independent variables that are categorical and a dependent variable that's numeric. All right. If a participant has 3 parking tickets, I want to predict how much happiness they will have in March. What test will I use? Well, if you're looking at the word prediction and you have a specific number of parking tickets, basically you'd have to figure out the line of best fit or the regression line, and then use it to estimate how much happiness somebody would have in March. So this is going to be basically a simple linear regression, or just called linear regression. I think that your GPA is associated with how many parking tickets you have. What test would I use? Anytime you see a word like related or associated or something like that, you're talking about just general relationships between variables. That's going to be a correlation. Correlation. Okay. If I think that students who live on campus have a higher GPA than students who live off campus, what test am I going to use? Well, you got 2 different categories of people, and they're different groups, right? Like people, you can't live on campus and off campus, I don't think. So you either live on campus or you live off campus. So that means there's 2 different groups of people, and we're comparing an average GPA basically. So this is going to be an independent samples t-test for sure. If I know the population has an average of 3 parking tickets, and I know, or I think that my sample has significantly fewer parking tickets than the population, what analysis will I use to test this hypothesis? So we're comparing a sample parking tickets to a population parking tickets. We're given the population mean, but not the population standard deviation. So that's going to be a one sample or a single sample t-test. If you were given the population standard deviation for parking tickets, then of course it'd be a one sample z-test. Okay. Um, if I think that students who are in the chess club have a higher GPA than students in the other two clubs, what analysis will I use to test this hypothesis? So remember, right, there's three different psych club, chess club, yoga club, three different levels. And if I'm comparing them on some numeric dependent variable, well, that's a one-way ANOVA. That's a one-way. One-way ANOVA means one factor, one independent variable with any number of levels. In this case, it happened to be three levels. Okay. If I think that your both your GPA and number of parking tickets predict your happiness in March, what analysis am I using? Okay, GPA and parking tickets are both numeric variables. There's two of them, two independent variables, and you're trying to predict happiness in March. Well, that's a multiple regression, right? Multiple regression, more than one predictor variable. All right. I know that the population has a mean GPA of 2.0. I also know that the population standard deviation is 1. I think that this sample's GPA is significantly higher than the population's. Which analysis do I use? Well, if you've got the population mean and population standard deviation, that's going to be a one sample Z test, right? One sample Z test. Okay. I think that students who have more happiness in January than they do in March. What analysis is that? Well, you don't have different groups of people. It's all just the same big group of students, and you're comparing that same group across two different time points. That's going to be a paired samples t-test. Again, it doesn't have to be repeated measures across time, but oftentimes you do see that. It could just be the same group of people measured that you're trying to compare on two different numeric variables, but most often you see something like this, before and an after or something like that. Okay, I think people are happier in March than they are in January. Calculate the estimated standard error. Okay, so this is the same question. It's just actually kind of reversed. So this is saying I think people are happier in March than they are in January. That is a paired samples t-test or dependent samples t-test. Calculate the estimated standard error. All right, let's go find the equation for that. Boop, 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 boop. Here we go. Okay, this is a dependent samples t-test or paired samples t-test. You're looking for the d bar, which is the mean of the different scores, divided by standard deviation of the different scores over the square root of n. Well, which of these parts is estimated standard error? Well, it's the entire denominator is estimated standard error. The entire denominator is called estimated standard error. So I need to find the standard deviation of the different scores and divide it by the square root of the number of people in my sample. Standard deviation over the square root of n. Let's do that. So we are talking about happiness in January and happiness in March. I'm going to make a new column called difference. And again, I look at the question, how it's worded. It says, I think people are happier in March than they are in January. March than they are in January. So I think I'm going to take happiness in March and subtract happiness in January, because the idea would be that overall I'm going to try to get a positive D bar, positive um, t-score if I was going to do the whole thing. But the question isn't asking for the whole thing. Like, I'm not actually going to have to calculate the t-score, it doesn't look like, just the estimated standard error. And what we need again for estimated standard error was the standard deviation of these different scores equals STDEV dot S. For the different scores, we get the standard deviation. Now, the estimated standard error for this is just simply going to be well, I guess I skipped a step. Let's do the square root of n real quick. Square root of n equals SQRT is the function. N, there's 16 people in the sample. So there you go. Okay, we've got square root of n is 4 people. Now to find the estimated standard error, all you have to do is take the standard deviation of the different scores divided by the square root of n, and boom, we've got estimated standard error of 0.90. 0.90. Whoops. Okay. I think that people without a car will have a higher GPA than people with a car. Calculate pooled variance. All right, well, what are we talking about here? People without a car versus people with a car. Those are two separate groups of people. Comparing in terms of GPA, that's an independent samples t-test. We're going to calculate the pooled variance. So let's go find where that is. Here we go. These are the three equations generally that you need to calculate an independent samples t-test. But for now, we really only have to calculate this pooled variance right here. So we need the sums of squares and the total degrees of freedom. Sums of squares and total degrees of freedom. Sums of squares. Okay. So what do you need to do? Well, you need to actually separate, car and GPA. You need to separate car and GPA, okay, into people who have a car. I'm going to say car yes, and I'm going to say car no. And we need to separate these out in terms of their GPA. So thankfully, it looks like it just alternates yes, no, yes, no, yes, no, yes, no, all the way down. So that's going to help us out. In terms of GPA, we're going to have 3.4. That's a yes. Then we're going to have 1.5. Then we're going to have 2.2. And then we're going to have 3. And then 2.2, 3.8, 4, 2.9. For people who don't have a car, it looks like we're going to go with 2.5, 2, 2.3, 3.6, 3.7, 3.9, 3, and 3.5. Okay. All right. So we separated out all the GPAs for people with a car and people without a car. In order to find the estimated, or no, I'm sorry, the pooled variance, well, the first thing you need to do is we're going to have to find deviation scores and then find the sums of squares. So in order to do that, we need the means. We need the means first, equals average. We need the mean GPA for each group, equals average. Find the mean. Okay. So it looks like people without a car might have a higher GPA, but we don't know if that's significant. We're going to find the deviation scores. Deviation scores. How do you do that? Equals the first score minus the mean for that category, or that group rather. Put in some dollar signs, drag that down. Do the same thing over here. Equals the first score minus the mean. Put in some dollar signs. Drag that down. Okay, we've got the deviation scores. Well, what do we do with them? Well, we're going to find our sums of squares. Sums of squares equals SUMSQ. Grab the deviation scores. Over here, same thing, SUMSQ. Grab the deviation scores. This is squaring them and adding them together. That's literally what sums of squares means. Okay, so now let's go back to our equation here. We've got the sums of squares. We're going to have to add them together for both of the groups and divide it by the total degrees of freedom. Degrees of freedom, you can do this two different ways. Either for each group, how many people are in that group minus 1, plus the other amount of people in the other group minus 1, or just everyone in the entire study minus 2, which is probably easier to remember and to do. So let's go through that. Okay, pooled variance. Pooled variance equals the sums of squares of group 1 plus the sums of squares of group 2 divided by, well, I'm just going to go the number of people in the study minus 2, n minus 2. We know that there's 16 participants, so 16 minus 2 is going to be 14. Okay, pooled variance 0.63. Nice. Now, obviously, you can go on to calculate estimated standard error, and then you can calculate a t-score, but the question was asking for pooled variance, so we'll stop here at 0.63, 0.63. Okay, here's a new one. Well, it's not exactly new, but the probability of being right-handed is 90%. The probability of being left-handed is 10%. If there are 120 people in a room, what is the probability that at least 20 of them will be left-handed? Okay. This is going to use this equation over here, where we're using basically kind of a binomial distribution to estimate the standard normal distribution, and you can get a z-score from this. But so this is actually pretty much the same thing as this, but now we're talking about probabilities, and so we have to do the observed number of people who are left-handed minus the expected number of people, which is the number of people, excuse me, the number of trials or the number of people in the room times the probability of them being left-handed, and then divided by this square root of the number of people total times the probability of success times the probability of failure. In this case, probability of success is the probability of being left-handed. Probability of failure is probability of being right-handed. So if we want to, I'm going to take that over here. We can just do this kind of off on the side if we want to. Um, you can just do this on a calculator, and honestly, I might recommend that you do that, but let's go fill these numbers in. So we've got 90% for right-handed, 10% for left-handed, 120 people in the room, and 20 people. 20 people is going to be what we think is going on. Okay, well, let's just start with the numerator, and then we get the denominator and put them together. See what we get. So the numerator is x minus n times p. X is going to be the number of people that we think are going to be like the number of people we observed, which is 20 people being left-handed in the room. And we're going to subtract the total number of people, which was 120, times the probability of being left-handed, which is 10% or 0.10. Okay. Hopefully you see how that's happening. X is the observed minus the expected. This is basically the sample mean, essentially. The number of people total times the probability. So that's what we would expect versus what we actually see. So, oops, I didn't put an equals in there. Let's put the equals there. We get 8 on the numerator. All right. Now we're going to go with the square root equals SQRT of the number of people, 120, or this is the number of trials. If I ask you like about coin flips, this is n is the total number of trials, times the probability of success. We said is the probability of being left-handed, so that's 0.10, times the probability of failure. That's the probability of being right-handed, which is 90%, so 0.90. Let's find that out. Okay, so then the z-score is just going to be equal to the numerator divided by the denominator, and we get a z-score of 2.43. 2.43. What is the probability that at least, okay, 2.43. All right, so that is the z-score here. And basically, you could, if you wanted to, then look up the z-score, compare it to an alpha of 0.05 if you wanted to do that. Okay, so let's see. What is the covariance between cookies and pets? What is the covariance between cookies and pets? Actually, you know what? Yeah, why don't we go well, just for practice? We got the z-score, but to find the actual probability, let's look up the z-score and then figure out the probability associated with that, because the question is not asking about whether that's significant or something like that. So let's go to the z table and look up a z-score of 2.43. 2.43. Okay, so we're going to go down and down and down and down and down. 2.43, here it is. That's the z-score. The probability of obtaining that or higher is the smaller portion. Probability is 0.0075. So we're going to go um, probability equals 0.0075. Okay, there we go. So this is the z, but the probability is 0.0075. All right. What is the covariance between, okay, we've got new data. What is the covariance between cookies and pets? Then it's going to ask us for the R, that's the correlation coefficient. So we're looking for covariance and correlation coefficient. All right, let's go look at that data. So first of all, what's covariance in the first place? This long equation here, you're basically taking the deviations of the first variable, multiplying them by the deviations of the second variable. You add those all up, you divide it by n minus 1, and then you can get the correlation coefficient, which is the covariance divided by the product of standard deviations. So let's go take a look. Maybe we'll copy these two things into, this is some new data. Some new data, and this is interesting. We're not given raw scores, we're given deviation scores. So that's gonna throw kind of a wrench in things, but also make it more interesting for sure. So it looks like we've got different psychology and business majors, and their deviation from the sample means on sleep, how many cookies they eat, and the number of pets that they own. All right. So, what do we need to do? Let's go back and we're talking about covariance between cookies and pets. Cookies and pets. All right, very good. So, we've got the deviation scores. We already have what's inside here and what's inside here. We need to multiply those things together and then add them up. So, we're going to go deviation products. Deviation products is what this is going to be. Basically, that's just equal to cookies times pets. That's what we're looking for, right? Yeah, cookies times pets. Drag that down, and you're just going to go the sum of products equals SUM of all these. And we've got a sum of products of negative 17. That's not the covariance, though. The covariance is going to take the sum of those products and it's going to divide it by n minus 1. So that n looks like there's 5 people. So I'm going to go equals this divided by n minus 1 would be 4 people. And we get negative 4.25 as the covariance. Okay, negative 4.25. Negative 4.25. Now it's saying, okay, calculate the correlation coefficient, R. All right, so right here, we've got R. We need to take that covariance and divide it by the product of the standard deviations for cookies and the times the standard deviation for pets. Well, how are we going to get standard deviation? Because these are not raw scores. I can't just do the function for standard deviation. Okay. But if you remember, deviation is actually part of the calculation for standard deviation, right? So deviations is this inside part. Well, if we square those and add them together, this is now the sums of squares. Divided by n minus 1 gives us variance. And the square root of that is going to give us standard deviation. So why don't we bring that right over here? Okay. So, all right, what we're going to have to do is for deviation for cookies, we've got the deviation scores already. We're going to square them and add them together. That's going to give us the sums of squares. So equals SUM SQ. This is the sums of squares. Equals SUM SQ. This is the sums of squares for pets. Okay. If you divide the sums of squares by n minus 1, you get the variance. You get the variance. Okay, so we're going to get the variance for both of these. So that's going to be equal to the sums of squares divided by n minus 1. Again, there's 5 people, minus 1 is 4. Equals this divided by n minus 1. 5 people minus 1 is 4. We got the variance. Okay, but that's not the standard deviation just yet. Standard deviation is the square root of that, SQRT of the variance. Boom. Equals SQRT of the variance. Okay, so now we've got our standard deviation of x and our standard deviation of y. And now we can finally get our Pearson's R, correlation coefficient, which is going to equal our covariance that we found divided by this times this equals negative 0.99. Wow, that is a very strong negative correlation. So for whatever reason, the more cookies you eat, the less pets you own, is what that would be suggesting. Okay, so negative 0.99. Okay, here we go. I'm gonna just drop this down a little bit so that we can see what's going on here. If I sleep for 3 hours, how many cookies do you predict I will eat? Okay, predict. That means we're talking about a linear regression. If I sleep for 3 hours, all right, so sleep is going to be the predictor variable. Cookies is going to be the outcome that we're trying to predict. It's going to give us the means, okay? It's going to give us the means. So we've got sleep and cookies now. We've got sleep and cookies. Well, let's go over here. Sleep and cookies. Now we're interested in covariance, the slope, and the y-intercept, okay? A is the y-intercept. So now I'm going to drag these two over. Just, you don't have to do this part. Like me dragging these over is how it helps me, but you all should just have a cheat sheet right next to you with all these written down. Okay, so I'm going to pop this over here. We're interested in these. So now we're talking about sleep. Oops, did it again. We're talking about sleep and cookies. All right. So we're going to need new deviation products, okay? And you might label this even further to help you differentiate it from the other deviation products. You can do it like, sleep and cookies or whatever helps you. Okay. So this is going to equal sleep times cookies. Going to get deviation products. We're going to have to add those together. Sum of the deviation products. Then the covariance is equal to that over n minus 1, and n minus 1 is 4. Okay, so that's covariance. Now we're going to get the slope. Okay, the slope is going to be covariance divided by the variance of x. Well, in this case, sleep is the variance, so we need to figure out the sums of squares, and then we can get variance after that. So the sums of squares is literally SUMSQ for sleep. Sum of the squared deviation scores. Variance is that sums of squares divided by n minus 1, which is 4 again. So now we have the variance. So that, I'm just going to put in variance of x right here. We know is 2.8. I just copy that over basically. And now we can find the slope. The slope or B is going to be equal to the covariance that we just found divided by the variance. And we've got a slope of negative 1.5, which indicates that the more sleep you get, the less cookies you eat, essentially. Okay. So we've got the slope. Beautiful. Now we need to get the y-intercept. What we're trying to do is get towards the line of best fit, the equation for the line of best fit. So I need the A. I need A. That's the y-intercept. So how do I do that? Well, I have the slope now, and I need the means. I need the means. Well, again, these are raw scores. These are not raw scores. They're deviation scores. So you can't just find the mean very easily. But thankfully, in the question itself, we're given the answers. They're given the means. So sleep is 4.4, cookies is 4.6. I'm just going to put mean sleep 4.4, mean cookies 4.6. Okay. So our y-intercept, y-int, or you could put A there for the y-intercept, is equal to the mean of y. And remember, the mean of y here, the outcome, y, is cookies. So the mean of cookies minus, and then in parentheses, slope times the mean of x, which is our predictor variable, which is sleep. Here's the y-intercept. Beautiful. And so if you were going to make the line of best fit equation, it would be y hat. Remember, y hat is predicted value of y equals, mx plus b, right? But now it's bx plus a for whatever reason. So that would be the slope. Um, that would be, we're doing slope times x plus a, right? So that's just what it would look like. And if you go back, it says, hey, I sleep for 3 hours. So how many cookies are we talking about? Well, you would substitute in here the slope times 3 cookies plus the y-intercept. So why don't we do that? Um, y in this case, or the predicted value of y, should actually be y hat. Y hat. No, no, no. No, I didn't want that. Thank you, Excel, but no, thank you. Okay. So that's going to equal the slope times the raw score, which was 3 from the prompt. And we're going to add the y-intercept. And so we would expect, did it again. You would expect if you sleep for 3 hours, then you eat, then you eat, oops, no, 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 no. Then you eat 6.75 cookies. 6.75 cookies. 6.75 cookies. All right. Very good, very good. Here we go again. All right, for the next few questions, refer to this scenario. I'm studying how reading the textbook and using flashcards affects GPA. I go to a dorm and measure how many hours each student reads the textbook, how many flashcards they study, and their GPA. When I run my statistics, I get this output. Okay, we got a lot of stuff going on here. What kind of test is this? Well, just from the prompt, we're talking about flashcards and textbooks, reading of textbooks affecting GPA. That's multiple independent variables, and they're measured in numeric intervals. So we got hours and we've got how many flashcards. So this is going to be multiple regression, right? Definitely multiple regression. What is the number that represents the effect of both textbooks, well, reading the textbooks and flashcards on GPA? That's going to be big R right here. Big R is going to be that number. Okay. Does reading books alone predict GPA? Another way you could say this is, does reading the textbook controlling for flashcard use predict GPA? So you look at textbook and you go over to the p-value, and it looks like, yeah, reading the textbook controlling for flashcards, the p-value is less than 0.05. So yes, it does. How about flashcards controlling for textbook? Where you go to flashcards, you go p-value is 0.93, that's above 0.05. So that does not independently predict GPA. Okay. All right. Very good. Let's go. Okay. For the next 4 questions, use this output. All right. How many main effects are you testing in this output? So if you aren't familiar with this, what this looks like is the main effect of phone on some dependent variable. We're not told what the dependent variable is. The main effect of car on some dependent variable, and the interaction between phone and car on the independent variable, or I'm sorry, the dependent variable. So that looks like what? A factorial ANOVA, right? And a factorial ANOVA, in this case, we've got 2 factors, phone and car. And so you need to do a test for main effects of each one, main effects of phone, main effects of car. So there's going to be 2 main effects plus the interaction effect. Okay. If this said how many overall effects, there's going to be 3 overall effects that you're testing. But here, there's 2 different main effects and an interaction. Which of the effects are significant? Well, you just look at the p-values. Um, Main effect of phone, that is significant. Main effect of car, that is significant. 1.8 times 10 to the negative fifth is a very small number. And the interaction, 0.0015, all three of those, we would say, I'm just going to put X as if I was checking a box or something. Yes, all of those are significant. What is the mean squares between for car? Okay, mean squares between is going to be this blank right there. To figure out the mean squares, you just take the sum of squares and divide it by degrees of freedom. Sum of squares between divided by degrees of freedom between. If we look over here, that's this part right here. So mean squares between is the sum of squares between divided by degrees of freedom between. If you wanted to know the degrees of freedom, how to calculate that, that's the number of levels of the variable minus 1. All right, so let's go back. What's the mean squares for car? All right, you would take 425 divided by the degrees of freedom, which is 1. Well, guess what? That is 425. What's the F value for the effect of car? Okay, so if we just figured out that this value here is 425, okay, I'm going to populate that in, and you want to find the F value, you need to take the mean squares between, which is what we just found, and divide it by the mean squares within, which is corresponds to this residuals. That's also called error sometimes. So you just take 425 divided by 12.8. You can just do that on a calculator. You can do it on Excel. You can do it however you want. You can't see me doing this, but I'm just going to calculate this on a calculator in my phone. So 425 divided by 12.8. And again, where did I get this from? The F ratio or F value, you take the between groups variance, which is also called mean squares between, divided by the within groups variance, which is also called mean squares within. So mean squares between divided by mean squares. Mean squares between divided by mean squares within, mean squares between, mean squares within. There we go. I got 33.20 is the F value. 33. Okay. Last couple of questions here. This is a separate question. This is not anything to do with the previous output. What is the critical value of a z-test if you have a two-tailed test with alpha is 0.05? Okay, you can just memorize the critical values of z because they never change no matter what the sample size is. The critical value of a z-test where you have a two-tailed test and alpha is 0.05 is always going to be positive 1.96 and negative 1.96. And you could put in either of those and they would be correct. If it asks for a one-tailed test, you would put in one-tailed, that's 1.64. Or if you're looking at the bottom of the distribution, then it'd be negative 1.64. But let's go figure out how I came up with these numbers. You would go to, in the case of a two-tailed test with alpha is 0.05, you remember you have to split alpha into each of the tails, so it becomes 0.025. Well, if you go looking for 0.025 in the as alpha, as the p-value essentially, 0.025 is right here. You follow it across, the corresponding critical z is 1.96 or negative 1.96. Both of those are true in a two-tailed test. For a one-tailed test, you're looking for the 0.05. There is not an exact 0.05 for alpha or the p-value here, but most people use 1.64 for whatever reason. Okay, very good. And last question, what is the critical value of t for an independent samples t-test when n equals 12? Well, you have to know how to calculate degrees of freedom for an independent samples t-test. In this case, n minus 2. That's something you should write down. For a one samples t-test, for a paired samples t-test, n minus 1. For independent samples t-test, n minus 2. So n minus 2, we got 12 people. That's going to be degrees of freedom of 10. And we're talking about a two-tailed test. Alpha is 0.05. So we go to the t-table. And we said degrees of freedom was 10. Two-tailed test, alpha is 0.05. 2.228. 2.228. 2.228, right? Okay, very nice. So overall, what you're going to want to do You don't have to have this in an Excel, unless that's helpful for you. You could just have all of these equations written down on a piece of paper right next to you. We didn't do this, converting a correlation coefficient into a t-score, and then you could compare it to a t-critical on the t-table, but you might be asked to do that on the exam. So just so you know, basically anything's fair game. Everything that we just covered is going to give you a good head start. We didn't fully calculate an actual observed T and compare it to a T crit, but you might have to do that on the exam. So just be comfortable with all of the different kinds of tests we perform. On the exam, I will not have you actually perform ANOVA tests, but I will have you interpret output. So just so you know. Okay, that's it for this. Best of luck on the final. Have a good one.